When the power of sine is odd, save one sine factor, convert the remaining factors to cosine. Step 2, if the power of cosine is odd, save one cosine factor, convert the remaining factors to sine. Now these are for the integration problems that have a combination of sines and cosines, and each one can have varying powers. These are not necessarily set in stone, but they're just good recommendations. If both powers, and this is step 3, or tip 3 really, when powers of sine and cosine are even, then you can use power reducing formulas. Either this one, if you run across an even power of sine, you can convert it. These are half angle identities that have been modified a little bit, squared on each side. If you happen to have an even power of cosine, then you can use this expansion to help solve your problem. And what it'll do is it'll convert odd powers of cosine after you get those done, and then go back up to step 2. But anyway, let's jump into examples. And these steps, again, they're just tips to help you get along. We have the integral of sine cubed x, cosine to the 4th x, dx. Because we have an odd power of sine, this would be like tip number 1. I'm going to take these 3 sines and rewrite them as 2 and 1. So that's why I wrote over here, save a sine. Now, sine squared through the Pythagorean identities from your trig can be rewritten as 1 minus cosine squared x. If we let u, and this is after distributing, if we let u equal cosine x, its derivative is negative sine x. Isolating sine x dx, which was the outermost part, we get negative du. So negative du, cosine to the 4th x becomes u to the 4th, cosine to the 6th x becomes u to the 6th, because that was our substitution. The antiderivative, will be negative u to the 5th over 5 plus u to the 7th over 7 plus our constant of integration. Since this is an indefinite integral, our u gets replaced with our original substitution, so we have negative cosine to the 5th x over 5 plus cosine to the 7th x over 7 plus c. The integral of cosine cubed x over square root of sine x dx can be worked out using some of those tips from the first slide. Specifically, what I want to do is, since I've got an odd power of cosine, I'm going to save a cosine. That way I'll still have all 3. I've got 2 of them in the main fraction, 1 of them over here to the side. Sine x under a square root could be written with a power of half. Pythagorean identity lets us change cosine squared x to 1 minus sine squared x. Splitting into 2 fractions with a common denominator, 1 over sine x to the half, we bring our sine x to the half up, and it becomes sine x to the negative half. The other fraction, using the same denominator, is negative sine squared x over sine x to the half. 2 minus a half is 1 1/2, so that's sine 3/2 split into 2 fractions with a common denominator. And when you reduce, you get these 2 terms. We still have the leftover cosine that we saved in the beginning. Let u be our sine x, and so that translates to u to the negative half minus u to the 3/2. The derivative of sine x is cosine x dx, so since that's our leftover, that's our du. The antiderivative, add 1 to the power, that's u to the positive half. Dividing by half is the same as multiplying by 2, minus Add 1 to the power, that makes it 5 halves. Dividing by 5 halves is the same as multiplying by 2/5, plus our constant of integration. Now we return sine x back into the problem and replace the u's. So we have 2 square root of sine x, or leave it as a power of half, minus 2/5 sine of 5 to the 5 halves power, plus our constant of integration. If this happened to have been a definite integral, and I put this side note, if you had been asked to approximate a definite integral, you work it like it's an indefinite integral, but instead of keeping the plus c, you sub in the top limit and bottom limit of your integral. Now let's see how that plays out. Sine of pi over 3, so that's 2 sine pi over 3, which is square root of 3 over 2, to the half, minus 2/5 sine of pi over 3, that's still square root of 3 over 2, so minus 2/5 square root of 3 over 2 to the 5 halves. When you substitute 0 in for sine x, you get 0. Sine of 0 is 0. So that's why I wrote this note out here. Type this into your calculator, and you can approximate the value as 0.239. The integral of cosine to the 4th x dx, 4 is even, so we can use that power reduction formula from the first slide, tip number 3. Cosine to the 4th x, that's cosine squared times cosine squared x. Replace with the power reducing formulas. I'm going to pull these 2's out. 2 times 2, that's why I'm pulling out a 1/4. Foiling the numerator, you get 1 cosine 2x, another cosine 2x, and that's the O and I from FOIL. So that gives you 2 cosine 2x. And then the last is cosine squared 2x. The first two terms you can get the antiderivative pretty nicely. The antiderivative of 1 is x. The antiderivative of 2 cosine 2x is sine 2x. If you don't trust yourself, take the derivative, see if you get that term back. The derivative of sine 2x is cosine 2x times 2 from chain rule. Now I distributed the 1/4 out here to the far right, so I'm not integrating or taking the antiderivative of this yet. When you distribute, you get 1/4 cosine squared 2x dx. These first two terms, we got the antiderivative just fine. This has an even power, so once again, I'm going to use a power reducing formula. This time, be careful to note we have a 2x for our angle, and in the expansion, it's double whatever angle is in your problem, so that's why this 2x becomes a 4x. This x becomes a 2x, so 2x doubled is 4x. Pulling out the half, or the 2 on bottom, gives us 1/8. Our numerator is still 1 plus cosine 4x dx. Everything in the front half of the problem has stayed the same. We've already finished it. It's getting this last integral. 1/8 times the antiderivative of 1, which is x, gives us 1/8 x. The antiderivative of cosine 4x is 1/4 sine 4x. 1/4 times 1/8 is 1/32, plus our constant of integration. The first and third terms, they're like terms. 1/4 plus 1/8, that's 3/8 x. And then our second term and our last term, we just recopy. Wallace's formula, you will see this come up again in Calculus 3. It doesn't take long to cover it. It's a straightforward calculation. You have two situations, And this is for definite integrals from 0 to pi over 2. It can be for cosine to any positive power or sine to any positive power. Whatever the power is, like in our first example, we have cosine to the 7th power. That's your n value. And what that tells you is you'll slowly build fractions starting with 2/3, and that's because 7 is odd. We're looking at the first expansion. 2/3 times 4/5 times 6/7, but the number in your exponent is the last number you'll write down. Once you reach this number, you quit expanding. The product of these three fractions reduced is 16 over 35. Again, these top two properties work whether you have sine or cosine. So the integral from 0 to pi over 2 of sine to the 6th, which is even, that's property 2. We start with 1/2 and we build up until we reach that bottom number matching our power. So we're going to go 1/2 times 3/4 times 5/6. We reached our number 6, so we quit expanding. And now the even one has a pi over 2 multiplier. The first one does not. The product of these three fractions is 5/16 times pi over 2 is 5 pi over 32. This is just the first of 2 videos for trigonometric integrals. I didn't want to do a video that was super long, so this is part 1. Let me know if you have any questions. Email, phone, swing by the office, or ask in class.